All right, so 4.2a today. Kind of strange. Skipping 4.1 for now. And in 4.2a, there's a theorem called the mean value theorem. And the way theorems go is they start with an if, and then they have a then. And they say that if this stuff is true, then this happens automatically. So all you have to do is verify to see if these are true, and then you get this stuff for free in the then. All right, so the two requirements for the mean value theorem are, number one, f needs to be continuous on the interval a, b. So maybe A is 1 and B is 7. And that means that it's a nice connected graph between 1 and 7. It could be discontinuous in other places, but at least on that range, on that interval, it's going to be continuous. And then number two, f needs to be differentiable on the interval AB as well. But notice there's a really subtle difference there. There can't be any corner points or vertical tangents, etc., in between A and B, but there could be a corner point at A, at the end point. So it just has to be differentiable on the numbers in between. There's not brackets there. That's on purpose. Okay, so for the mean value theorem to apply, it has to be continuous and differentiable on an interval. Okay, so here's what happens. Then there is a C on the interval AB. And I'll give you the rest of the punchline in a minute. But I just wanted to start this because this is an existence theorem, right? It's saying that something exists. We had one other existence theorem earlier, and we'll recap that after we talk about this a little bit more. But this is saying that if this stuff happens, then C exists. Doesn't necessarily tell you what it is. It just says it exists somewhere in between A and B. All right, so here's the scenario. We have a graph, f of x, and in between A and B, it's nice and smooth and connected. It's continuous and it's differentiable. And it's just saying that there's a number C somewhere in between A and B. Okay, here's what happens at C. There's a C on A and in between A and B with the slope at C equaling, and what I'm going to write down here is the average rate of change, but I'm going to write it in the math way. The average rate of change is f of B minus f of A all over B minus A. Okay, so what this is saying is that somewhere the instantaneous rate of change is equal to the average rate of change. In other words, somewhere the slope of the tangent is equal to the slope of the secant. Okay, so let's see if we can find that place on this graph, because apparently it exists according to that theorem. So we need to look at the average rate of change between A and B. So it's the slope between those 2 points. The slope of that line that I just drew is this number right here, the slope of the line. This is just y minus y over x minus x, right? Average rate of change. Okay, so apparently, according to this theorem, there's a place where the slope at C is equal to that slope. So try to picture where that is. Where on here is the slope at C equal to that slope? So it looks to me like right about here, the slope of the tangent is equal to the slope of that other line. And also, I guess there could be a second place. This theorem doesn't say there's not two, it just says there is one at least. There could be another one right here. I don't know exactly how this graph goes, but it's possible there's a second one. You could argue with me whether that's actually a tangent. But for sure, there's one there that equals that. Okay, so this is C right here. It's the x value where the slope of the tangent line is equal to the slope of the secant line. All right, so we're going to practice with that. We're going to have f of x equals the natural log of x minus 1 on the interval 2, 4. And we're going to show that f satisfies the hypotheses of the mean value theorem. And also find C. I don't understand why you guys are wearing camouflage that works in the woods. This is a school. I mean, I wore camouflage that works here, right? You can't even see me. I was going to put aluminum foil on my belt, and it would have been even better, but I ran out of time this morning, so. Because then it would have matched up with the... Okay, so we got to show that f satisfies the hypotheses of the mean value theorem. And fine. When I saw it was camouflage day, I was like, yes. All right, so to show that it satisfies the hypotheses, this is a fancy word, hypotheses. It just means the if part of the mean value theorem. So we got to show that it's continuous and differentiable. And we're going to do that informally. So we're just going to graph this. So just pop it into your calculator. So I think it goes through 2, 0. Actually, I'm pretty sure about that. So because 2 minus 1 is 1, and the natural log of 1 is 0. Okay, so it goes through 2, 0. And then it's got a asymptote there at 1, which you can't totally see maybe on your calculator, but it does. Okay, so there's the graph. So this is not a continuous graph everywhere, right? There's not even points over here. There's a problem at 1. But definitely from 2 to 4, it's continuous. So connected on 2, 4. So continuous. Now we're just doing this informally, so let's remember the official way to prove that something's continuous. What's the official definition of continuous? been a long time. It was chapter 2, week 2. Yeah. So a function's continuous at A if this happens, right? You take the limit towards A, you take the function value to A, and you hope they're equal. And if they're equal, then it's continuous at A. So I don't want to forget the formal. But on this problem, we're just saying, hey, look at the graph, it's continuous. All right, and then also, if you look at this graph, there's no corner points, no vertical tangents, and what's the third one? No cusps. Good. So that means it's differentiable on 2, 4. So no corner points, cusps, or vertical tangents. On 2, 4. And I guess I could even put brackets on this one, but I want to make sure I remember that it just needs to be parentheses for the theorem, for the differentiable part. Okay, and then that's informal, which is fine on this problem. But let's remember, how do we show that something's differentiable at A? If we wanted to do it officially. Take the limit as x goes to A of f of x minus f of A all over x minus A, right? And if that limit exists, then it's differentiable at A. So that's the formal way to show that it's differentiable. Okay, so now we have shown, informally, that f satisfies the hypotheses of the mean value theorem. So according to the theorem, there must be a c that does what that says it does over there. And so now we're going to find that c. Okay, so we need to find where the slope of the tangent line is equal to the average rate of change. So I'm going to start out and calculate the average rate of change. So that's f of 4 minus f of 2 all over 4 minus 2. So that's the ln of 3 minus the ln of 1 all over 2. ln of 1 says e to what power is 1? It's e to the 0 power, that's 1. So that's 0. So the average rate of change is the ln of 3 divided by 2. And if I wanted to get a decimal, I could, but I'd rather try to stay exact. All right, so that's the slope of the line connecting those 2 points. It's this, here, I've got a picture, so why don't I use it? That's the slope of that line. Okay, so now I need to find the place where the slope of the tangent line is equal to that. So I need to calculate the formula that'll give me the slope of the tangent line. That, of course, is the derivative. So f prime is, so the derivative of the natural log of something is 1 over the something, right? So this is 1 over x minus 1. And chain rule is kind of necessary. I could times by 1 here, but it's not that big a deal. The derivative of the inside is just 1. Okay, so there's my derivative. And apparently, according to the theorem, there's a number c where the derivative at c, that's the derivative at c, right? If this is the derivative at x, then that's the derivative at c. Apparently, there's a place where the derivative at c is equal to the natural log of 3 divided by 2. There's a place where the instantaneous rate of change is equal to the average rate of change. And I had already calculated my average rate of change. So now I'm going to try to solve for that x value where they're equal. So then you cross multiply. So we got 2 equals natural log of 3 times c minus 1. Then divide the natural log 3 to the other side. So c minus 1 equals 2 divided by natural log of 3. So c is 2 divided by natural log of 3 plus 1. So I was trying to be exact throughout that problem, and I accomplished it. But I'd like to know what this number is. So now let's round it to 3 decimal places. 2 divided by ln3 and plus 1. So what do we got? Kristen, what you got there? Okay, sorry. Sorry to pick on you. 2.82? We need 3 decimal places. Good. Does everybody agree with that? All right, cool. So that kind of looks like it's right. Because 2.8, I can buy that. That's where the slope of the tangent is equal to the slope of the secant. Okay, so that's the mean value theorem. It talks about where the slope equals something. Yes?
Where'd you get the C minus one?
I just plugged the c into the derivative formula. So this formula is identical to that formula, except I'm talking about a particular number now, where x represents any number, and c represents the particular number that I'm trying to find. So it's not a big, I mean, you could put 1 over x minus 1 here, and it would be the same thing. Good. Okay, so that's the mean value theorem. But earlier in the class, it's been a few weeks, we had a theorem called the intermediate value theorem. So since it sounds so much like the mean value theorem, it's going to be easy to get them confused. So that's why I'm going to talk about this one right next to it. Okay, so the intermediate value theorem was an if-then thing again. And it was an existence theorem. It said then there is a C on AB with f of C equaling something. So this is a big difference. This is the y value equaling something, right? As opposed to over here, this is the slope equaling something. So the mean value theorem is an existence theorem. It says that there's a place where the slope is something, and the intermediate value theorem is an existence theorem. It says there's a place where the y value equals something. But they're both existence theorems, and they're both called value theorems. Okay, so there's an f of c that equals the y naught. So I have to remind you what the y naught was. The y naught is any number in between f of a and f of b. That's where we get the term intermediate value. Because it's the middle number. So intermediate and middle, that's what's going on here. Okay, so the why not had to be a y value in between these, and the second requirement was that f had to be continuous. On AB. Okay, so these are both existence theorems, so it's easy to get them mixed up. That's why I'm putting them next to each other. Okay, let's see what else I got here. Well, one thing I want to talk about is back to this. So the Pennsylvania Turnpike, it's a interstate that goes through Pennsylvania, the south part. And it's a toll road. Has anybody been on it? It's long, right? Aaron's like, Aaron, I asked if anybody been on it, and Aaron was like, yeah. Because it takes forever to get across Pennsylvania on the Pennsylvania Turnpike. Okay, so on the Pennsylvania Turnpike, you enter the road, and they give you a ticket. And then when you get off, they're going to charge you for being on the road. It's a toll road. Okay, so what they do is they give you this ticket, and it has the time on it. Let's say you got on the highway at 2 o'clock in the afternoon at mile marker 100. So 2 o'clock, mile marker 100. And then you get off the road 2 hours later at mile marker 300. Your average rate of change, you went 200 miles in 2 hours, right? So your average rate of change was 100 miles an hour. It's pretty fast, right? It would make the trip better, maybe, as long as you didn't pass away during the journey. Okay. Okay, so your average rate of change is 200 miles an hour. That's this, right? I just did this. Your average rate of change is 200 miles an hour. You are sitting at the toll booth, paying your toll. You're not moving. Your instantaneous rate of change is 0, right? But the policeman can come to your car and hand you a ticket because he says, I know calculus. Your average rate of change was 100 miles an hour. And I know that that means that somewhere during your trip, you were going 100 miles an hour. Your instantaneous rate of change was 100 somewhere. I know that they have done this. I'm not sure if they do it now, but I know that the toll roads have done that. Handed people tickets just based on their average rate of change. It's legal, it's held up in court, but people argue, obviously, right? What are you talking about? You didn't see me going 100. Well, we know that even though they didn't see him, they were going 100 at some point. Okay. Let's see. I would like to talk about something if I can find it. Yes. So this is solving inequalities. And we're going to look at 3x squared minus 13x bigger than 10. Okay, so whenever you solve an inequality, the first step is to solve the equality instead. That seems kind of counterintuitive. So I'm going to solve for when this equals 10, rather than for when it's greater than 10. All right, so to solve for this equal to 10, I need to subtract the 10 over. And then use either quadratic formula or factoring. I think factoring works on this one. So you put a 3x here and an x here. And let's see, a 5 here and a 2 here. Because this is negative 15 and positive 2. So that comes out to negative 13. So then you set each parenthesis equal to 0 by itself. So 3x plus 2 equals 0. And also x minus 5 equals 0. So x is negative 2/3, x is 5. Okay, so the reason we found where it equaled 0 is because those are the possible switching places. If I want to know when it's bigger than 0, if I move the 10 over, right? If I want to know when it's bigger than 0, it might switch from bigger to 0 to less than 0 when it hits 0. And also it could switch when it's undefined. But this problem isn't ever undefined, so I don't have to worry about it. So maybe let's write this down. Possible switching places. Are when it equals 0 or when it's undefined. So anytime you solve an inequality, this is what you need to do. You need to find out when the mess is undefined, which doesn't apply to this problem, and you need to find when the mess is equal to 0. That's why we set it equal to 0 first. And the key is that if it's going to hit 0, if it's going to switch from above 0 to below 0, it's either going to cross over 0 or it's going to jump. So it's either going to cross over or it's going to jump. All right, so negative 2/3 and 5, back to this problem, are the possible switching places. So to keep our thoughts organized, we're going to mark those on a number line. Those are the places where this function might switch from being positive to being negative. Okay, so really what I care about is when this is bigger than 0, right? So I'm going to test a number in between negative 2/3 and 5 and see what happens with that number. So a really easy one to test is 0. So I'm going to take 3 times 0 squared minus 13 times 0 minus 10. Okay, I cannot emphasize enough that you have to show this work. You've got to write it down. You can't just pop it in your calculator and say you did it. And that's not for me, that's for the AP test. Okay, so this work right here, you got to write it down. It's probably worth 2 points in May. Definitely 1. Okay. All right, so that comes out to negative 10, right? Is that bigger than 0? No, it's not. So that means 0 is not an answer to this, and thus not an answer to this. 0 is not an answer. Since 0 is not an answer, I know that none of these are answers because it doesn't switch in there. I found all the possible switching places. So since it doesn't switch in there, 0 is a representative of all of those numbers. So if it doesn't work for 0, it's not going to work for any of them. So to say that it doesn't work for those numbers, I put an X there. So I'm sorry to belabor this point, but you might accidentally leave this out and just put an X up there, right? And it's not completely right because you're not showing your work. Yes? So what I mean is this quantity here, I'm trying to figure out when it's bigger than 0. And I found out that 0 doesn't qualify. And in between negative, and I also found all the possible places where the quantity switched from positive to negative. Because the only way it can switch from above to below is crossing 0 or being undefined. And during this interval, it doesn't cross 0. And it's not undefined. So if it's below for 0, it has to be below for all of those numbers because it didn't switch during that. I feel like we're now 93% there. Chew on it and then ask another question in a few minutes. Okay, so now we're going to test 6 to represent all of these numbers. It'll be easier to test it here, actually. So since I'm being so careful about showing my work, or since I'm telling you to be careful, I better be careful myself as well. So I'm plugging 6 in there. So that's a positive number times a positive number, which is positive. So I can get away with being lax here as long as I'm not being lax up here. So that means this does work because 6 is bigger than 0. The 6 outputs something bigger than 0. And so therefore all of these numbers work because 6 represented all of them. And then I'm going to try -1 to represent these numbers. That's a negative number times a negative number, which is positive. So that is bigger than 0. So all of these numbers work. Yes? Yeah, it does. It's 3 minus -13. So we're comparing to 10 now, since you went back to this one instead of 0.
Yeah.
Good, I got you. Good. I like to use this one, though, because it's easier for me to compare to 0 than 10. But it's the same thing. You could you go back up here if you wanted to. Good. Is everybody else okay? Okay, so the final answer is that this quantity is going to be bigger than 10 for all x's from negative infinity to negative 2/3, and then also for all x's from 5 to infinity. Okay, everybody's still totally fine. We got plenty of time. Okay, that's all I have for today. Thanks for listening.